Hello everyone, hope you're doing well. Welcome back to my channel. Today we are discussing the solutions for the weekly contest 422 which happened on 3rd November, which is a Sunday. Okay, 3rd November 2024. So in this particular challenge, basically I've already discussed the first question. So in this particular video, I will be discussing the second question. And if you have seen my previous video, you will get to know that in this particular contest, basically the second and third question are related. Okay, so if you are able to solve the second question by default, you just have to add one or two sentences extra in their code, and you will be able to get the solution for the third question also. So in this particular video, I'll be showing you the solution for the second question. Okay, it's a medium level question. Let's see the question now. It's question 331. Find minimum time to reach last room. Okay, it's the first part of it. Yeah. So coming to the question, there is a Dangion with n into m rooms arranged as a grid. Okay. So basically, you are given a two-dimensional grid where n and m are the in dimensions. Okay. You are given a 2D array move time. Okay. So this is going to be your input. Okay. It's going to be a array 2D array called move time. Okay. Of size n into m where move time of I of j represents the minimum time in seconds when you can start moving to that room. Okay. So try to understand this. See, this part is going to be the most crucial part in this question. Okay. So only this part. Okay. The only single input is given, you have to understand everything here. Okay, so see, if you're talking about this particular index, okay, first of all imagine, okay, though it is looking in a 1D array, but basically it's a 2D array, right? So if you see this thing, what happens is we will start here. Okay, in the question they will be mentioning this, that we will be starting at 0 comma 0 and this is going to be 0 comma 1. Okay, so the idea here is you can start moving towards this room at t equal 4. That is, you will start moving, you will not reach this room at t equal 4. Okay, for example, if I want to go from 0 comma 0 to 0 comma 1, so I will have to, from 0 comma 0 I will start at 4. Okay, t equal to 4, and by the time I reach here it will be t equal to 5. Okay, that is the basic idea here. Okay, so just I want you to understand this part. Okay, you will not reach that at t equal to 4, you will start going towards that at t equal to 4, and you will reach this particular room at t equal to 5. Okay, that's what you will get to know here. Okay, so where move time of I and j, okay, I comma j represents the minimum time in seconds where when you can start moving to that room. Okay, remember this word start moving, they've also highlighted it. Okay, that's very important, otherwise the whole calculation will be wrong. Okay, you start from room 0 comma 0 at t equal to 0. That's what I was saying. Always you'll be at t equal to 0, you'll be at 0 comma 0. Okay, and move and can move to any adjacent rooms. Okay, when this adjacent, it basically means either horizontally or vertically. Okay, here the diagonal movement is restricted, there is no such possibility of a diagonal movement. Okay, only the horizontal direction or the vertical direction. When I say horizontal, it means both left and right, and when I say vertical, it means both up and down, right? But there is no diagonal movement here. Moving between adjacent rooms takes exactly 1 second. Okay, that's what I was saying here. See, if you are at t equal to 0, okay, so at t equal to 4, that you are at 0 comma 0. Okay, at t equal to 4 you will start moving towards this particular index. Okay, where is 0 comma 1? By the time you reach it, it will be t equal to 5. Okay, because it will take exactly 1 second to reach that room. Okay, because the adjacent rooms. Okay, exactly 1 second. Return the minimum time to reach the this particular node. Okay, what is this node? This node basically is the, you know the bottommost, right bottommost node. Okay, that is the basic idea here, the right bottommost node. Okay, this particular node. Okay, two rooms adjacent if they share a common wall, either horizontally or vertical. That's what I was trying to say you. There is no diagonal movement possible here. So coming to the first example here, and see the question how it is different. See, other cases what we had is, we used to have like, let us say this particular room has a distance from here, like the distance between two rooms, this like that they used to say. But here they have changed the question, they are saying the minimum time, okay, in seconds when you can start moving towards that room. Okay, otherwise you cannot move, as simple as that. So for example, it is t equal to 4 here. So if you are at t equal to 3 or t equal to 2, you cannot start moving, cannot start moving towards this room. Okay. So at wherever you are, if you have to enter this room, okay, it has to be after t equal to 4 only. Okay. And it will take +1 to reach this room. Okay. From any adjacent wall, any adjacent room. Okay. So by the time you reach it will be by minimum 5 seconds here. Okay. And by maximum, it can be anything more than that. Okay. So if you can simulate this particular thing, so by the way, you have to start at 0 comma 0 and you have to end here. Okay. Okay, this, okay, I will just quickly, make the diagram here and I will show you, because that will be more clear to you. Okay, these, it's how it will be looking. Okay, 4 and 4. Okay, yeah, so you are at here first of all. Okay, at, if you have to go to here, there are only two possibilities, right? From here you have to move towards this. Okay, otherwise from this particular 0 you can move to this 0 4 and this 4. Okay, either way it's going to be the same approach only. So what you have to see, you are here, right? First of all, let us say want to travel to here. So because the waiting time is 4, what I have to do, I have to wait till t equal to 4. I'm at this 0 comma 0 only. Okay, I am at 0 comma 0. Okay, till t equal to 4. Okay, then I start moving towards 0 comma 1. Okay, by the time I reach 0 comma 1, okay, it is t equal to 5. Okay, already 5 seconds have gone. Okay. Now, what is the waiting time for this? Is again t equal to 4. Okay, that is 4 seconds. First 4 seconds, which I have already crossed. By the time I'm here, it is already 5 seconds. Okay, so I don't have to wait to get into this. Okay, I can start as it is. Okay, the time I reach in this 0 comma 1, I can start towards this one. Okay, which is 1 comma 1. Okay, so by the time I reach 1 comma 1, it will be t equal to 6, and as they have shown here, it can be shown that this is the minimum time that it will take to reach this particular node. Okay, remember what I did? I went from 0 comma 0 to 0 comma 1, and then I came to 1 comma 1. Okay, you could have also done from 0 comma 0 to 1 comma 0 and then to 1 comma 1, but here, since the waiting time here for this node and this node is exactly same, so it doesn't matter which route you take. But yeah, in when we are getting a bigger array, here there are only 4 elements, but if you are getting a bigger array, obviously those things will also matter. So just I wanted to tell you like how this thing is different from any other question. Here basically this is a waiting time. Remember, this is not something to travel. Okay, this what doesn't mean that you will take 4 seconds to travel from this room to this room. That is not the case. Why I'm saying that? Because see, from this comma 0 comma 0 to 0 comma 1, it took if you see here, it took this much time. But from this thing, okay, from 0 comma 1 to 1 comma 1, it did not take any much time. Okay, it did not take any such time, but only 1 second gap. Okay, because 1 second to travel to adjacent room. So this is how it is different. You see, if had this been the magnitude, that is, had this been the distance, okay, to travel to this room, it should have been 0 to 4. Okay, this is fine. But when you move from this to this, you would have to add 4 again. But here that is not the case. Once you cross t equal 4, you can come here directly by just with the within 1 second you can come here. That is the basic idea here. Okay, that is something that I want to tell you. Okay, fine. Now I've already, yeah, let us jump back to other examples. Okay, so they have explained the same thing here, and there are two ways to go there, and they have explained both the approach, and you will get 2 equal 6 in any of the ways. Okay, now this is the other one. Okay, okay, let me draw this also and show it to you, because see, in this particular question here, imagination is very important, because only if you can imagine, you will be able to code that solution. Okay, so again, let me zoom in this. Yeah, so here what is happening, is by the way the second example. Yeah. So here I am at 0 comma 0. Okay. Okay. I have to reach this particular index. Okay. So what I have to do, see here, waiting time is 0 for everything. Okay. So in this case, this question becomes the shortest path. Okay. You have to use any shortest path algorithm, whichever way you want, you can do it. And you have to reach this particular node. Okay. The bottommost right node. Okay. That's the basic part. So what I have to do, let us say I go from here to here to here like this. And then from here, I travel to this. That is the basic idea. So what I'm doing, from here to here, it is taking 1 second. Okay. From here to here, it is taking another 1 second, and from this particular node to this particular node, it is taking another 1 second. So total, I guess we are having 3 seconds. So here, that's why the answer is 3. Remember, here all of them are 0. That means there is no waiting time for any of the nodes. So for because of that reason, we have to follow the shortest path algorithm, and you are getting this. Okay, you could have also traveled to this. Okay, from this particular node, you could have done, you could have come here, and then you could have traveled horizontally. That also is possible. Okay, so that is the basic idea, and the third example, you can go through it on your own. Okay, so if you talk about the constraint that we're having, so n is okay, so it is at max, it can be of a 50 to 50 array. Okay, the grid can be 15 to 50, and the move time, okay, here it doesn't matter much how much the move time is going to be, but it is of the range 0 to 10 power 9. Okay, that is something that we have to consider. Okay, let me comment out this as well. Okay, fine. Now, so I've already explained to you how this question is different from any other question, because see, you cannot use simply shortest path algorithm, or you cannot use the DP approach, especially because I've wasted a lot of time trying the DP approach. That's why I want one in the starting itself. See, this is not something, why DP is not possible here is, see, here we cannot break this question into sub problems. Okay, why I'm saying this, because here the concept of time is also there. Okay, here the concept of starting time is also there. For example, here we cannot say that, for example, if I reach here, you will be thinking that why don't I take this as a sub problem and start finding the DP value of this, and so that DP value could be like from here to the this particular node. Okay, how much time it will take, so that I can add to the starting node and I can get the answer. See, this thing we cannot do it here, because see, the path that you're going to take, that also contributes some of the time, right? Based on that time, basically you have to decide whether you are going to add this waiting time to that path or not. That is the basic idea here. Okay, so this waiting time will only apply till t equal to 4. If you have crossed t equal to 5, that is crossed t equal to 4, and you are reaching this node, then you don't have to add anything more. Okay, the case that I've shown here, see, from you are here to here, if you see, I'm not adding anything extra. Okay, I'm just adding 1, which is the time to travel from that node to this node. Okay, I'm not adding any waiting time there. Okay, so that is why this question is different from all those questions. Here we cannot take break this particular question to sub problems. Okay, that is something that I want to tell you. So how to do this question? Here, the kind of traversal that I will be using is, it's a BFS traversal. We'll get to know that how we are doing that, but it's a BFS traversal. We will like considering all the possibilities that we have, and we'll be taking the one, okay, which is having the smallest start time. Okay, wherever the arrival time is the smallest, we'll be taking that and we'll be proceeding. Okay, so what I'm doing, so first of all, I'm calculating the both x and y elements. That is the x dimension and the y dimension here. Okay, I'm calculating both of them. Then yeah, I'm creating an array. Okay, I am calling it as a DP array, but it will not function as such a DP array. It's just acting as a cache. You may also call it as a cache, but I just name it as a DP because previously I was taking the DP approach. But yeah, you can also call it as a cache array. Okay. Okay, this particular array will record the arrival time at each particular node. Okay, so initially all of them will be float of infinite. Okay, that is infinite time because I've not passed to that node. But yeah, as by the time we reach every node, we'll be making the updates here so that we can store the arrival time, and we will be basing the node in the second time only if the arrival time is smaller than the previous time. Okay, as simple as that. Okay, so its dimension is going to be same as that of what we had in the grid. Okay, same as that of the move time. Yeah, that is the dimension of this. And the first, okay, because see here what is happening is you are clearly given that you will be reaching 0 t equal to 0. Okay, so here the, yeah, for 0 it's already fixed. Okay, the arrival time. So for that reason I am marking it as 0. Next, what are the movements possible for us? Okay, here the diagonal movement is not possible. For that reason I am already saving all the dimensions possible, all the directions possible. Okay, this is the horizontal direction. Just a second. Yeah, this one refers to the horizontal direction. This one refers to the, okay, horizontal direction towards the right. This one is the horizontal direction towards the left. This one is the horizontal direction. Okay. Okay. Yeah, this one is the horizontal direction towards the right. This one is horizontal towards the left. This one was vertical direction towards the, okay, you can say bottom. This one is the vertical direction towards up. Okay, above that. I'm storing in the movement array because I will be using this later on. Okay, and now I'm declaring a minimum heap. Okay, min heap. What min heap basically means? It means that the always the zeroth index will have the smallest possible element. Okay, in this case, each element is going to be a tuple. Tuple basically means that the way you have a list. Okay, here it will be a tuple. Okay, so what is the tuple? So each value here means something. Okay, this particular value tells me the arrival time at x comma y. Okay, and what are these things? This is going to be the x. Okay, this is going to be the y coordinate. These two are going to be x and y coordinate, and this particular value. Okay. Okay, let me zoom in and show you. Okay, these two are going to be the x and y coordinate, and this particular value is going to be the arrival time. Okay, at x comma y. This is going to the min heap. Okay, min heap. I hope you understand. Heap concept basically means that at 0th index will be having the smallest value. Okay, so whenever you are doing, you are entering something, already the sort will happen, and whenever you are referring the 0th value, 0th index will always the smallest value. Now I'm doing this. Yeah, I'm doing this while loop. Okay, this is the while loop. This loop will run till we have a single entry present. Okay, till the single element is present in the min heap, this loop will continue. So what I'm doing, I am first of all, yeah, popping out any value that is there. Okay, remember, when I say heap pop, it basically refers to the 0th index value, okay, which is the smallest value. And now you will be asking me, what does the smallest value mean when we have a tuple like this? Okay, each element is going to a tuple like this. So what is the smallest value? See here, whenever you have a tuple in Python, okay, especially the library that I'm importing, the heapq library, okay. So what will happen is always this particular index will be considered for this sorting purpose, okay. So the first element, that is the 0th element in this min heap, is going to be the one which is having the smallest arrival time, okay, smallest arrival time. That is the reason why when I say heap pop, it will be popping out the element. It will be 0th element, and it will be the one which is having the smallest arrival time. Okay, so I'm storing the current time of it. The current time basically means the arrival time at this particular index. Okay, which is at x comma y. Okay, x comma y. That's why I'm storing it as x comma y. I'm popping it out and I'm storing those values in this variables. Okay, current time x and y. What I'm doing, first of all, I'm checking. Okay, if x limit and y limit are there. Okay, that is if I have reached the node that I'm destined to. Okay, in this case, this particular node. Okay, n minus 1 ka m minus 1. Now remember that, okay, I will come to this condition in a win because you will not understand it. It's important now. You may be asking why I'm checking it here, but I will let you know this why I'm doing this here. But for now, let us skip it. Okay, what I'm doing next, I'm doing with the moving, that is this particular, I'm trying to, for the current x comma that I have, I'm trying to explore all the possibilities. Okay, where all I can go. So I'm going through I comma j of the movement array, and I'm calculating the new x and the new y. Okay, what I'm doing, simply I'm adding I. These are the I comma j, right? These are going to the I comma j. Okay, in each case, in each of the cases, these are going to be the I comma j. I'm calculating the new x by adding I to it, and similarly I'm calculating the new y by adding j to it. Okay, j to the previous y, similarly I to the previous x, I'm adding it. I'm calculating the new x and new y. What I'm doing next, now I am declaring another variable called the arrival time. Okay, because remember, this was the arrival time at x comma y, but now we have to calculate the arrival time at new x and new y. Okay, so initially I'm initializing this arrival time with the current time. This is the first thing. Okay, next what I'm doing, Next, I'm checking whether this new x and new y are within the range of this grid or not. Because see, if they're out of the range, for example, if you see here this particular node, okay, okay, let me do this here. If I am at this particular node, I cannot go above it, right? With the above element, first of all, there's no element above that, and it is out of the grid, so it should not be crossing the grid at any moment. Okay, that is the basic idea. Yeah, I should not be crossing the grid at any moment. Okay, so yeah, this is the one. So I'm checking whether this new x in the range of x limit, that is, it is within 0 to x limit minus 1. Okay. Similarly, this new y should be within 0 to x limit minus 1. Only if this is true, this part of the code will be executed. As simple as that. If it is not true, that means we are having an element which is outside the grid. So yeah, because the movement that we have coded here, that led us to a index which is outside the grid. So we can simply ignore it, because that is not possible to explore that index, right? We can simply ignore it. So this part of the code will not be executed for such cases. What I'm doing next? See, now I have a valid index. Okay, once I coming to this part of the code, that is, once this for if condition is satisfied, that means this new x and new y is a valid element, and we have to explore it now. Okay, first of all, we'll calculate whether we have the enough wait time to reach there or not. Okay, so if the move time of new x and new y is greater than the current time, okay, what is the current time? Is basically the arrival time that we are having. Okay, it's the current time. Current, see, at this part of the code, both of them are same. Okay, remember that. So I'm checking them whether the move time of new x and new y is greater than the arrival time, that is, if I can enter that or not. Okay, if that is greater, that means I cannot enter it currently, so I'll have to wait till I reach this particular time. Okay, so what I'm doing, if it is greater, I am assigning the arrival time to this value. Okay, see, because it was greater, right? It's greater than my current arrival time value, that is my current time. So what I'm doing, I am assigning the arrival time this value. Okay, because we'll have to wait. For example, you saw here, right? Here it is 4. Okay, so I cannot move here till the t equal 4 comes. Okay, I cannot move here till t equal 4 comes. So I will be making my current time as t equal to 4, and then I will be adding 1 to it, because 1 is for traversing to that node, right? That's what we'll do next. So here I'm making the arrival time is equal to this particular thing. Okay, remember, only if it is greater that we are doing. If it is not greater, this part of the code will not be executed. Simple as that. Next, what I'm doing, I'm adding 1 second to move between the adjacent room. Okay, so arrival time plus equals to 1. Okay, that's arrival time is equal to arrival time plus 1. Next, remember, now there is two cases. Okay, either we have visited this new x new y again, that is, previously also visited this new x new y, and we are visiting it again. That could be a possibility, right? So for that, what you have to do, we have to check whether this arrival time, okay, it is less than dp of new x and new y or not. Now, where is this dp coming? This is the one which we have declared here. If we have not visited this previously, then its value will be float of infinite. Okay, it will be float of infinite. Then obviously this new value, this new arrival time will be less than the infinite value, so we will be proceeding here. But there will also be a case where this could happen, that we have visited this node previously also, but we are visiting it again, but this time the arrival time is less than that. Okay, for that reason we are checking it once. Only if it is less than the previous dp value, that is the previous arrival time that we had for that node, if it is anything less than that, only then we will be proceeding further now. Okay, otherwise we'll not be doing that thing again, because if it is greater than or equal to the previous arrival time, that means again like a circle, right? So we'll not be going into that circle. Only if we are getting a better arrival time for that particular node, that is new x and new y, only then we will be, doing this part of the code. What is this new part of the code? First of all, we will be changing the dp value to the best arrival time now. Okay, because this arrival time is better than the previous arrival time, so we will be changing it now. Okay, next we will be pushing this particular element to the heap. Okay, this is the element that is going to be pushed into the heap. What is this element? It's going to be the arrival time, that is the new arrival time that we have for this node. Okay, and the new x and the new y. Okay, these are the x and y coordinates of that. Okay, now we will come to this part of the code. Okay, this part, why I am doing it here. Now remember that, let us say there will be multiple nodes which will be reaching the, okay, this particular thing. Okay, that is, and this is the last, that is the target node. Many, we can reach this target node through multiple ways, right? But remember, what is happening here is the thing which you will not be appreciating till now, is that we are using a minimum hoop. Remember that. That's why you will see here we are doing a heap push. Okay, so what will happen is, once we push the node, okay, it will automatically sort it. After the push operation, it will be automatically sorting the node, and the next node which will be popped out will always be the one which is having the least arrival time. Remember that. So the idea here is, let us say multiple nodes which are reaching to this particular node are inserted into the heap, but the first, okay, whenever we are doing a pop, remember that, that is whenever we are doing this pop, it's always the smallest arrival time that is being popped out. Okay, so if we are popping this particular index, okay, that is, we have reached this node and this thing is getting popped out, that means this is having the least possible time among all the other things that are pushed into that heap. Okay, that is why if we are reaching this node, that means we have reached the answer. I'm returning it. Remember, anything after that, okay, any other node after that will be either having the same time or a time greater than that arrival time. Remember that. Otherwise, this would not have been popped now. Okay, anything that will be popped after this, okay, after this will be having at arrival time greater than the current time. Okay, so that's is the reason why this is going to be the smallest time in which we can reach the target node. That's why we'll be returning this time. Okay, that is the simple logic here. Remember, the only thing we have to learn here is the minimum heap concept. Okay, minimum heap, whenever you're pushing something, automatically it is getting sorted. Okay, the sorting is based on the arrival time in this particular case. Okay, so whenever we are reaching this target node, that is, this target node is getting popped out, that means this is going to the best arrival time here, because it is having the smallest arrival time. That's why it is getting popped out compared to all other cases that we have in the heap. Okay, that is the reason I am returning the current time here. Okay, and if I can zoom out and show you, remember, after I come out of this while loop, then we see the only two cases when we are coming out of this while loop. First thing is when the minimum is over. Okay, the other case is when we're returning it. Okay, so when we're returning it, obviously we'll not be executing this return statement then again. Okay, but remember, once we count this value, I'm returning this. Remember, this return statement ideally should never be executed, because there will always be a way to reach the target node. In this case, okay, there will never be a case we are not able to reach the target node. Okay, so that is the reason why whenever we are reaching the target node first, I am returning it. See, this part I am sure that you will be having doubt, or most of you will be having doubt, but the reason here is, see, let us say there are 5 ways to reach the target node, but since all of them are present in the heap, remember that only the smallest value, okay, only the all among all of them, whichever way is having the smallest arrival time will be popped out first. So ideally, whenever I'm having x and y which is equal to the target x and y, and the arrival time is assured to be the smallest, okay, that is the reason why I should be returning it whenever I'm getting it popped out. Okay, that is the basic idea here. So yeah, this ideally will never be reached. Okay, this statement will never be reached ideally. Okay, so yeah, and that was this question. This was a really nice question, because the kind of way they've given it, right? This is very different from every other question that we have seen. Usually, what we can do is, we can solve using a DP approach, where we can divide into sub problems and we can solve it. But in this case, this is not possible. Why? Because see, this is going to be the time delayed. Okay, that is the time you can start moving towards that node. Okay, it will depend on the path that you are taking. That's the first thing. Second thing is that if for example here, as I've shown you, if I've already crossed equal to 4, then I need not wait here at all. So that depends on the path that I've taken. I need not wait at that node. Okay, if I've taken longer path, then I don't have to wait here. Okay, I can directly enter this. Similarly, I can directly enter this. That is the basic idea. But if you have taken shorter path, you may have to wait it here. So it's not like I can start from this particular 4 and reach here without knowing from how I came into that 4. Okay, so the path that I took to reach that particular 4 also matters in this case. That's why we cannot break them into individual sub problems and solve them. That is not possible in this case. That's why in this case, actually, if you see what we're doing, it's kind of a BFS approach, because that every new node that we're having, okay, we are seeing all the, see, this is the current x and y, right? From here I am trying all the possibilities, that is all the 4 directions I'm moving, and then if they are, I am like finding something better with a better arrival time, I am pushing into the heap. So it's kind of a BFS approach that I'm doing. Okay, I'm going level by level. Okay, for first level will be all the x and nodes to x and y, and then on, like, similarly for those x and y, it will be inserted into the heap. Now among them, whichever is the smallest arrival time, that will be popped out, and for there the x and nodes will be inserted into the heap. That is the basic idea in this question. So this was a really nice question according to me. And if you have solved this question in the first go, okay, in the contest, really heads off to you. But yeah, I got to learn a lot in this question. Okay, it took really a lot of time for me to, because see, I was damn sure that it was a DP concept in the way I was solving it. But then I got to know that no, this problem cannot be solving that particular sub problem approach. Okay, we cannot break this into sub problem. And then ultimately I tried this and I got this answer. So yeah, that was all for this particular question. In the next video, yeah, this the third question is exactly similar to this. We will be making small change in this code itself to get the answer for the next question. So I will show you the same change in the next question. That was all for this video. See you tomorrow. Thanks a lot.